The next thing I want to talk about is Raman spectroscopy. Raman spectroscopy is a scattering process. I've got a diagram here, energy level diagram. So first off, if we take ourselves, look to the left, and we see the piece labeled infrared absorption. So these are vibrational energy states in the ground electronic state. And infrared absorption spectroscopy is simply, we're going to absorb a photon. Straightforward, the same thing that happens when we have something that absorbs light, and then the valence electrons go from one level to another. Okay. There's a process called Rayleigh scattering, which is the predominant process when I shine a light on something. By the way, this is the reason the sky is blue, because blue light scattered much more effectively than red light through Rayleigh scattering. So Rayleigh scattering, very, very few photons, the rare process. And what happens is that it's a scattering off of a virtual state. Virtual state meaning it's not a real energy state. It's a combination of other energy states. It's not something where now this is at electronic levels. It's not something that electrons going up to that state and then down again. This is not absorption and re-emission. It's a scattering. And with Rayleigh scattering, the light is scattered at the same frequency. Now, so Rayleigh scattering, if an object is transparent, maybe 1 in 10 to the 6th photons might get scattered, Rayleigh scattering. The rest are simply going to be transmitted through the sample. But of about 10 to the 6th less likely than Rayleigh scattering is that the the photon of incident light is scattered off of the molecule, but it leaves the molecule vibrationally excited. That is the Stokes-Raman scattering. So Stokes scattering is lower, so I find some new, I'm going to use a tilde on it, and this is going to be, my scattered light is going to be equal to, in energy, the nu 0, the incident light, minus nu 0 to 1. Okay, again, 0 to 1 are the vibrational levels I have here. So so the light is coming off with somewhat lower energy. The difference in energy is the energy of the vibrational of the 0 to 1 vibrational level. And so if I can take that visible light and see what its spectrum is that's scattered, I get the vibrational spectrum of the molecule, but now in visible light instead of infrared. There is one other thing that happens. It's much more rare. It's dependent upon temperature. And that is, if a molecule starts in an excited vibrational state, I can now scatter that photon off of that excited molecule, but now it returns to the ground vibrational state. And so now this is going to be the actual frequency of light is wave numbers, energy and wave numbers, is going to be equal to nu 0, the incident intensity, plus the intensity of the the energy of the 0 to 1 transition. Okay. The selection rule for Raman spectroscopy is that there must be a change in polarization. Now, polarization is a kind of a hard thing to visualize. Dipole moment is a little easier. We can visualize that a little easier. I'm going to pop up some selection rules and some fairly intense math in the next piece. We're not going to need to know it. For selection rules for Raman spectroscopy, now in this case, the direct product of the vibration and one or more quadratic terms, which I've listed this way with the P representation, must include the totally symmetric representation. So it's not the dipole moment operator, but it's quadratic terms. So quadratic terms must, now in what I do, I look at C2V, go back to my character table, that next column that I see, that next column, all of those quadratic terms say that all of these modes of motion are Raman allowed. So what can I do? I look at this and say, oh, in infrared, only A1, B1, and B2 are allowed, but in Raman, they're all allowed. In a centrosymmetric molecule, in a molecule that has inversion symmetry, it's either or. It's Raman allowed or infrared allowed. And there's not overlap between the two. Now, the last piece, totally symmetric modes, so in this case A1, have different polarization properties. That is, the polarization of the light that's Raman scattered is different than a non-totally symmetric representation. And so what I can do, I can take a spectrum of a fairly complex molecule, and by looking at the polarization properties, I can now assign, oh, these bands are due to the totally symmetric vibrations. It can be very helpful. Now, the intensity, here comes the math. Okay, the intensity is proportional to, first, there's a fourth order dependence upon the incident frequency. So the new Mn is the new 0,1 that I had earlier. So there's the cofactor up front, and then a sum over all, and this is a sum over all intermediate state. We're going to do, this is over all intermediate states. So the important piece is just realize that we're using a little bit different notation than we'd used before. We have the Stokes and the anti-Stokes, the nu minus nu zero, the nu plus nu zero, initial state, final state, the intermediate vibronic states. These are the electronic vibrational state. Cartesian coordinates. So we're summing over different Cartesian coordinates, which is why this is quadratic. We have dipole moment operator for 2 coordinates. And they effectively end up as coordinates squared. We'll come back to this in just a moment because there's one piece I want to highlight. There are two, well, one I'll highlight later. The first thing is that this increases as a 4th power of incident light frequency. Now you might think, well, I can go to really high frequencies and I increase the effect. You would be right, but you also increase many other possibilities. Fluorescence, which interferes, photoionization, all kinds of things that can happen that will swamp out your Raman signal as you go to higher incident frequencies. Some general ideas from Raman is quantum mechanical. The Raman intensity increases as the change in polarization with change in, so this, what is this? This alpha is polarization. It's those ugly looking integrals that I showed you earlier. Q are the normal modes we talked about in the last slide. So in Raman, stretching vibrations are stronger than bending, and symmetric stronger than anti-symmetric. This is opposite from infrared. In infrared, anti-symmetric are stronger. The piece about this, which is really interesting, is if I look at water, water is a horrible infrared solvent. The water bands absorb really, really strongly. It's a really good Raman solvent because the intensities, the Raman cross-section, the Raman signal that you get from water is really low. Example of equipment. So I take a laser beam, So my laser, this is my new 0. It comes in, it's a beam splitter. Now this beam splitter is designed that it transmits, it reflects the laser light, but it transmits light at longer frequencies, at less energy. So we take that, we focus it down onto our sample, the Raman scattering comes back off, we have a lens to focus it, we have a filter because remember the Rayleigh scattering is 10 to the 6 times higher, and so we need another filter there. We then just take that into a spectrometer. So we have a, this is a basic spectrometer. We have a great entrance slit, a grating, and then we use a mirror to refocus the light onto what's called a charge-coupled device. It's an array detector. It's similar to what you might find in your camera. Resonance Raman is a phenomena where the incident light comes into resonance with an electronic frequency. And so if you remember, we had this mathematical description here, was this goes to 0. The whole term becomes, so this one term becomes much larger. And so that enhances by many, many orders of magnitude. So this is going to allow us to study the chromophores of metalloenzymes. So among other things. So let's say I have a metal enzyme has iron in it and at its active site, or it's got a porphyrin in it, or it has some other copper, blue copper proteins where they in the absorption band. And now what I can do is at very low concentrations, 10 to the -4th, 10 to the -5th, 10 to the -6th molar, that I can take that protein in a very small sample, only 10 microliters, and I can get usable Raman spectra off of those without interference from other pieces of the protein. I've got an example because there's nothing like showing something you actually did yourself. Back in the day, I did when I had hair, I ran this spectrum. And so we start with oxygen 16. What I did, so if you see off to the left, there's a structure. This is looks like a porphyrin ring, except you notice essentially it's had two OHs added across one of the double bonds. These kinds of materials are called chlorines. Say it is a porphyrin derivative. In this case, the change, the electronic change, these are bright green, and this protein was bright green, bright emerald green. So if irradiate it, the thing we did was we either you can oxidize the protein either by fully reducing it and then adding oxygen, or by adding hydrogen peroxide. And when we did that with O16, we got the top spectra. And these numbers are frequencies, difference from the fundamental frequencies. So these are the vibrational frequencies. So notice we have a vibrational frequency at 815. We have a band at 815 nanometers. What happened then when we used oxygen 18 as an isotope? And there's this is only a small piece. This whole spectrum went way on from about 400 to out to 2,000 wave numbers or more. So when we instead oxidized with oxygen 18, what did we see? Well, we saw that a band shifted from 815 to about 770. None of the other bands shift of any notable amount. What does that tell me? That tells me that there's something about that band at 815 that involves oxygen oxidation. that's involved in the process. By the way, this enzyme is it's a bacterial terminal oxidase. So it catalyzes the reaction of O2 plus 4H plus 4 electrons going to 2H2O. Well, so we did that. Now the last piece was, there's a question with this. And the question was, this wavelength range would be appropriate for either a oxygen-oxygen stretch in a peroxide or an iron 4 bonded to an oxygen. Our first thought was that it was peroxide. So we'd have a peroxide bonded to an iron 3 and an O2 minus. Why? Because, well, mostly because this sort of iron 4 oxo species is not known to be stable. In any other protein, it was not known to be stable. What we discovered, though, was then we used a mixed isotope O16, O18. What will we have here? Now, this is not 1/6, it's a statistical mix. So the mixture is going to be 50% 16, 18. And then 25% each, 16O, 16O, and 18O, 18O. If that were the case, if it were peroxide, we would then see a stretch, a band in the middle, right here. We would see 25% would be at 815, 25% would go to 769, and 50% in the middle. Well, there's no band there. And so that told us that this had to be an iron 4 oxygen stretch, even though it really violated conventional wisdom because these were not stable. And you notice this is sort of my highlight here. This was an accelerated publication and was the front page publication in biochemistry.